So identify one element that exists as a network structure. So you've got neon, which is a noble gas, so it doesn't even bond, so it's not A. We know that oxygen and nitrogen are both molecular substances, so we know that it's neither C or D. Carbon can form a covalent network substance in diamond or graphite, so we know that B is our answer. With reference to the bonding exhibited, explain why diamond is often used as coatings for high-speed saw blades. A lot of people will say, a lot of companies will say, our super awesome diamond blade has diamond coating and that is good for your sawing and things of that nature. Now the reason they have that is to increase the durability of the saw. Why is that? Well, this application requires a high strength material that doesn't deform easily. So you don't want it to deform because that's how blunting happens. So if you imagine this is what a blade looks like when you get very close to it, as soon as something hits it, it might get a little bit blunt, and that's because of deformation. So you can see it's getting blunter and blunter. But what you want is you don't want it to get blunt. You want it to be as sharp for as long as possible. So you use diamond because diamond doesn't deform very well. So diamond is an extremely hard substance due to the strong covalent network structure that it forms. So the fact that it forms this very strong covalent network substance means that when you have a very sharp point, it's not going to deform as much as another substance. Graphite, which is made from carbon, is electrically conductive, soft, and optically very different from diamond. What can you conclude about the structure of carbon atoms in graphite? The carbon atoms in graphite are bonded in a significantly different way compared to a diamond. They're bonded very differently to the way a carbon is bonded in a diamond. Since both are made from the same element, the fact that they exhibit such different properties implies the bonding is different, or the way they're bonded is different. The arrangement of atoms is different. In graphite, carbon atoms are arranged in two-dimensional hexagonal sheets. So they're formed like this, like that, hexagons, where each of them is C. Whereas, obviously in the diamond case, it's the three-dimensional form where each carbon is bonded to 4 adjacent carbons. And each of these hexagonal sheets, which I just drew, are weakly bonded to other sheets above and below it. So you essentially kind of stack sheets on top of each other and they're all weakly bonded together. And that's why a pencil works. Because when you draw a line on a pencil, what you're doing is you're leaving behind all these graphite sheets, and each of these sheets leaves sort of a black mark, which means that you've left a line. So you're leaving the carbon sheets behind as you write and draw with a pencil. By looking at the elements that form covalent network structures, what trends do you notice? Well, the semi-metals are the most likely to form covalent network structures. And it's probably because they have the most number of bonds. They can form 4 or 3 bonds, which means that they can form large sort of networks because they can make bonds with adjacent 4 atoms. So that's why they tend to form these network structures. This is due to the unique properties of their valence shell. Since many semi-metals have 4 valence electrons, they can form many bonds with adjacent atoms rather than forming a small number of bonds with one atom making a molecule or something. That's why they tend to form network structures. Because they can make bonds with lots of adjacent atoms, they can allow the network structure to develop. So carbon can form a maximum of 4 bonds. Explain why carbon cannot form a covalent molecular substance like C2. So how come you don't see C2, but you see O2 and N2, F2, and Cl2? Why is C so different? Well, for carbon to form C2, it would have to form a quadruple bond. So it would have to form 4 bonds so that both carbons are stable. This means that all 8 electrons will be concentrated into one section. If you imagine a quadruple bond, all of the electrons would be here. So that's 8 electrons, all in one small area. Because you have so many negative charges, the repulsive force would be really big, making this structure very unstable. So with 8 electrons sitting there, the repulsive force would be so big that the electrons would just repel each other and smash apart those bonds. So it doesn't make sense to make C2 because it'd just be so unstable. So that concludes today's lesson on common covalent substances. We looked at covalent molecular substances and also covalent network substances. And we saw examples of each and how they differ, and also what are some common examples that we see every day. So hopefully you've learned something. And in the next lesson, we'll be looking at using properties to sort of identify different bonding types. So I look forward to seeing you at our next lesson.